Let me briefly review the problem statement and then do the pre-analysis. Here we are given a heat sink shown in gray that's used to dissipate heat from an LED shown in green. And we are given a CAD file of the LED and the heat sink and an interface layer. There's an interface between the LED and the heat sink. And if I go to my ANSYS model here, there's the LED, and if I zoom in here, there's the interface between the LED and the heatsink, and then you have the heatsink in gray. And we're given the coefficient of thermal conductivity for the three parts in the assembly. We're given the heat generated by the LED. We're given the ambient temperature, and we are given the convection coefficient for the heat sink surfaces exposed to air, and that's necessary for the convection boundary condition to calculate how much heat is being lost through the gray surfaces. And we want to find the temperature and heat flux distribution in the model using ANSYS. And so the physical problem is conduction and heat sink, and ANSYS is not going to solve the physical problem. It's going to solve a mathematical model of that physical problem. So the first part of pre-analysis is to think about what is that mathematical model. So let's think about the mathematical model. The mathematical model is a 3D boundary value problem. Recall that when we did the 2D conduction tutorial, we had a 2D boundary value problem. So earlier we had a 2D boundary value problem. Now we have a 3D boundary value problem. And recall that the 2D boundary value problem looked like this. That was our governing equation. That's a heat diffusion equation in 2 dimensions without heat generation. We had insulated boundary conditions over here. We had an isothermal boundary condition at the bottom, and we had a convection boundary condition. Now for this problem, and before that, we needed to solve this boundary value problem to find the temperature as a function of x and y. Now what we have is a much more complicated 3D boundary value problem, but it's essentially the same animal. So what is the 3D boundary value problem for the heat sink? The domain over which we want to solve our governing equations is given by the geometry. So it's much more complicated than a rectangle, than the type of rectangle we had in 2D. And the governing equation for steady 3D conduction, so that's the steady 3D version of the heat diffusion equation, and you can see that over here. So you have derivatives in x, y, and z, and you have the heat generation term. So this is a 3D second order partial differential equation. And we need to solve that to find temperature as a function of x, y, and z, and then we know the temperature everywhere in this assembly. And to do that, we also need boundary conditions. And in this illustration, we have 2 types of boundary conditions. We have convection on the heat sink surfaces exposed to air that are shown in gray over here. And for those surfaces, essentially, the boundary condition looks like that. The normal derivative of the temperature is related to the temperature at any point on this gray surface through this equation. Okay, so it's a relationship between the normal gradient and the temperature at the point on the surface. And then everywhere else, we will assume that we have an insulated boundary condition, and the corresponding equation is that the normal derivative of the temperature is equal to 0. So we have a pretty complicated 3D boundary value problem, and we cannot solve this by hand, which is why we need to turn to a computer tool like ANSYS to solve it. So at this point, we have reviewed the mathematical model. Let's quickly review how the numerical solution strategy, relates to what we saw in 2D. So the numerical solution we obtain using the finite element method. That's what ANSYS is using. And we need to take our domain and divide it into elements and nodes as shown over here. So the elements are shown over here. There's a relatively coarse mesh, and you can see, I've highlighted 2 of the nodes over here. And we reduce the problem to determining temperature values only at the nodes. So if you have 1,000 nodes, we're going to determine 1,000 temperature values instead of determining the temperature everywhere else, everywhere in the domain. And then we use a polynomial interpolation to relate the temperature within an element to the nodal temperatures. So if I go back to my ANSYS model and turn on the mesh, and I can highlight, elements, and let me go to a wireframe view. So there's an element, and you can think of, the nodes in the simplest case as just the corners. So for the tetrahedron, you have the corners, and you'll determine the temperature there, and everywhere within the element you will use a polynomial interpolation. So obviously the interpolation has to be done in 3D, which is complex in its details. Similarly for this element, any element within our domain. And so how do we determine, the nodal temperatures? Because that's what now the problem has been reduced to. We start from the boundary value problem and derive a system of algebraic equations in the nodal temperatures using the element by element polynomial interpolation for temperature. So that's what the ANSYS finite element solver will do for us. And then once it, and the system of algebraic equations, one thing to keep in mind is, like in 2D, it'll relate a nodal temperature only through its neighbors. So if I write if I write an algebraic equation for this node, it'll relate the temperature only to its immediate neighbors. For instance, the temperature value far away from it is not going to come into that algebraic equation, which gives us a sparse matrix to invert. And when we invert that system of algebraic equations, we get the nodal temperatures. And once we have the nodal temperatures, we determine everything else, say, the temperature distribution within the model, heat flux distribution within the model, etc., through post-processing. So if I go in here and take a look at the, nice color plot of the temperature, red being hot and blue being cold, this is generated from the nodal temperatures through post-processing. So that gives you an overview of the numerical solution strategy